So now let us see a correlation example, a cross correlation example. As I was telling you, cross core is the function which we used even for autocorrelation, and we will use it for cross correlation also. So if at all you give two operands here, so it will be taking the first sequence, flip the second sequence, do the convolution, or it does the correlation. So what's the expression? Y of n, x of n into h of n minus k. That would be correlation. X of k h of n minus k is convolution. Okay, so I want you to take some very small sequence of length 3 and 4 and perform correlation on your notebook just to have a feel of it. Okay, because you should know, right, what the answer you got is correct or not. Okay, so shall we try? Nothing different in the program here, and not many properties really. There is this one property, a DFT property, which says that if at all you take the first sequence, a DFT of the first sequence, and multiply it with the conjugate of flipped conjugate of the second sequence, x conjugate of n minus k, and you multiply, you will end up getting circular correlation. You remember, you take the DFT of first sequence, multiply it with the DFT of second sequence. What you get is circular convolution. If I were to take the DFT of first sequence and multiply with the conjugate of x of n minus k, what you get is cross correlation. Okay, cross correlation. Okay, that to circular, that to circular. Okay, so that one property is usually can be asked sometimes. Okay, under DFT properties. Okay, so for the timing, let us see this thing. How do we run it? As I told you, every input gives you an answer, but it's all about giving some sensible inputs. Okay, so let me run this thing here. Since I'm not in the default directory, so let me select all these lines and let me manually run it using evaluate selection command. Okay, so it's asking me enter the sequence here. So what's the sequence? So let me give you a sequence. Okay, so let me see here. See 1, 2, 3, 4, 3, 5, 4, 6. Then 2, 4, 6, 8, then 7, then 8, then 0, then 3, then -2, -4, -6, -8, then 1, then 1, then 2, then 1, 2, 3, 4, then 2, then 3, then I've taken some sequence here. Okay, that's my first sequence. Okay, now let me take my second sequence. My second sequence is 1, 2, 3, 4. Okay, so as we discussed in the classroom, a correlation is where you have a sample and you want to relate whether whatever you have got in a bigger sample space, is there anything similar to what I have with me? Is there anything that is similar? Okay, so you are just going to check. So here, that's my task. So I have a sequence 1, 2, 3, 4, and I want to know whether there's a pattern of this 1, 2, 3, 4 here. Be it positive, you can see, be it negative, be it amplified, or be it attenuated for that matter. Okay, so I get to check it. Okay, so shall we? So I will run this particular thing. The values are there, fine. Okay, I got an answer here. As I told you, convolution and correlation are similar, but they are completely different. Convolution was commutative, right? The x of n convolved with h of n will give same answer like h of n convolved with x of n. It's not the case with correlation. It's not the case with cross correlation. Anyway, we have an answer here, an answer with prominent peaks once again. Okay, here also we have an answer with a prominent peak. Okay, so what is happening here? You can see, say, let us say this particular point is my 0 for the time being. Okay, this particular point is my 0 for the time being. And you can see for some reason, I have here a peak. Okay, what does this imply? This peak you can see, let me take you once again. I just realized that you are not able to see the figure window. Okay, so I will in a second. Before that, let me just show you what is here. Okay, you can see here my sequences. The similarity with 1, 2, 3, 4 is here in this part mode. Then it is here. So as and when you can see here, The first bit matches no, second bit matches fine, third bit matches, third digit matches fine. As and when all four matches, then bingo, we need to get a sequence. Then after 3 5, no 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 no, then you can see some match, some match, some match. Okay, bingo, second time. Then here match, some match, then yeah, here once again we have match. As and when the first sequence, whatever you want to try, matches completely with the second sequence, there is a very high prominent signal. Now let me show you the figure. Yeah, there's a figure. You can see this particular thing here happened in the first match where you got a very prominent peak. Then this one happened. Again, you can see the height of the second peak is much higher because the second time when we had a match, it was 2468. Same signal with the higher strength we got. Then again, there is a negative match here. This is because again, it's the same sequence. What negative indicates that the entire thing has one phase shift, but the pattern is same, right? The pattern is same 1 2 3 4 only, but it is ulta. Okay, so that was cross correlation. Now, if possible, if I will show you one more example. Okay, I will show you one more example. A typical radar case. Okay, so let us see. I think here, do I have it? Okay. So here we have a typical radar situation where in radars, what do they do is they send a known signal using a transmitter. Then they turn off the transmitter and turn on the receiver. Okay, they know what they're sent, and then what they do is they turn the receivers on and they keep on correlating whatever they receive with whatever they have. As and when there is a perfect match, it indicates that the signal has hit some obstacle and it has bounced back. Okay, if at all there is no match, then there is no obstacle. If there are obstacles 1 2 3 based on the amount of the strength, because the larger the pattern travels, the more attenuated it gets, the nearer it is, less attenuated it will be. Okay, so the pattern they usually use is called as a chirp. Okay, it's called as a chirp. So let me show you what is a chirp here. Okay, by executing this particular command. Okay, so let me just show you what is a chirp by plotting a chirp. Okay, wait a second. Once again. Okay, wait, I'm waiting for this. Yes. So here you can see this is a typical chirp signal. So what do you see here? So you can see a chirp signal is a wave which is linear frequency modulated. Okay, you can see the wave frequency is going on increasing very high, then afterwards goes on decreasing. Okay, some pattern, some known pattern, right? Different starting frequency, different end. It's this particular, it's a code for a particular radar, right? There can be several radars operating at any time. So each radar will have its own unique signal which it sends and says whether it's getting something in return. So this is a signal which I am taking for my example. Okay. So now what I will do is here you can see I have taken a way where in between some zeros I have put my pattern here. I call this particular chirp wave as a pattern and I have hidden that particular pattern here somewhere. You can see there is a pattern in here after some 400 samples. There is a pattern after some 250 samples. Again, I have kept a pattern. Then after some 700 samples, I have kept the pattern. And I have amplified the pattern in some places. Say I have multiplied it by 3 or 0.3, then some places 0.2 and some places 0.5. Okay. So to make the things much more interesting, what I have done is I have added a noise also here. I have added a noise also here. So let me just show you when I add the noise or before adding noise, how does the entire signal look like, right? Evaluating it. Okay. So wait a second. Okay. So here. Okay. So let me take you to the figure file. Okay. So here you can see this are my linearly frequency modulated or the chirp signals. Some wise I had given different strengths here. Okay, just to have a feel of what it actually happens. You can see the signals, whatever I have sent is in a very meager range. You can see between zero point 0.5, minus zero point 0.5 to 0.5. This one is between minus 0.2 to 0.2. This one minus 0.3 to 0.3. Things are all fine. It gets much more interesting when you have lots of noise while you receive. Okay. So to simulate that, let me add a noise, or I have added a noise in this particular program. You can see, and you can see the noise what I have taken, that also has the strength of around 0.2. Okay, so now let me show you the noise. How does it look like? Okay. So let me take you to the, wait a second, let me take you to this figure. You can see this here. Can you see this screen? Yeah, this is the figure, and this is the noise which I have taken, and this is the noise which I will be adding. Okay, so shall we? So added, sorry. Okay, so let me show you the figure now. Okay, so you can see the figure whichever I had drawn is a figure with the noise in it. Okay, it's the figure with the noise added. Earlier, when I simply showed you the figure with only the chirps, the signal looked good and you thought, what's the big deal? But when I added the noise, can you feel the impact, by the way, how difficult it might be? Okay, with our naked eyes, we cannot tell where is my actual signal, except probably in this particular place, because here I had given the strength of 0.5, right? But in other places, it is very difficult. Okay, so now let me just correlate. Okay, let me continue with the program, and I have, you can say I'm plotting here the correlation of my pattern with this particular signal, which is corrupted by the noise. Okay, so let me, yes, and let me take you to the figure page, and let us see what just happened. Okay, so as you can see here, there are the entire noise thing. The signal corrupted by noise was very difficult for us to check whether the signal which I sent was it there or not, because all of them were in the same range. But when you did the correlation, you can see there are prominent peaks. So as and when there is 100% match, you will get a prominent peak. Okay, you can see with this particular correlation approach, we have selectively found out whether the pattern which I sent is there or not, especially even in the presence of noise it has been carried out. Okay, so this is a very routine process in all the communication methodologies, where you want to synchronize, you want to identify an individual user, you want to separate individual users, right? You might need something like cross correlation. Okay, so that's that. Okay, let me end this thing here.